Hey, welcome back to Math with Patrick and Quill. Today is December 2nd, and we're solving problem 336 from the Daily Epsilon calendar. And the answer today, x, should be equal to 2 because the answer should match today's date. So we're just doing some polynomial division today, it looks like. We need to find the integer x where this polynomial divides that polynomial. Now, with polynomial division, there are a few strategies. We could just do long division. We sometimes can use synthetic division. And then finally, area models sometimes work too. Synthetic division is out because this one really only works when the thing we're dividing by is kind of like a simple linear factor. Quadratics kind of ruin the idea of synthetic division. Long division might be possible, but I kind of don't like it. And I think I'm going to favor the area model today. Before I do that, though, I do want to think of some candidate numbers for this x. And I think thinking about this in terms of multiplication first might help me come up with some candidate numbers for x today. Any division problem you can just rewrite as multiplication. And so I could think of it as t squared minus t plus x times something gives me my bigger polynomial. Now, knowing how polynomial multiplication works, it's pretty clear to me that the first term needs to be t to the power of 11, so that these two combine to be t to the power of 13. And then more importantly about the x at the end, the x and the last term here need to multiply and get 90. So this last number here is going to be 90 divided by x. And here this kind of shows me that we need some kind of multiple of 90 for x today. And so we could do maybe 1 or 90, 2 or 45, so on and so forth. Let me get this list down. All right, these are all the factors of 90 and therefore our candidate numbers here because we do have an integer for x. Now, integers can be negative, so that is a possibility to consider here, although I think I can rule it out with a kind of graphing argument here. This polynomial will have a y-intercept at that 90. The overall behavior will look like t to the power of 13, which is kind of like this, but then moved up 90 units. And this plus t basically will give us this kind of idea of a slope of 1 near our y-intercept, and then it doesn't really matter anywhere else because that t to the power of 13 is just so big. So our graph is going to look something like this. We only have one x-intercept, and so it's impossible for us to get two x-intercepts out of our quadratic. In that case, we would see two x-intercepts out of our degree 13 polynomial. So potentially our one root here comes from the quadratic, or the more likely case is that this one root comes from this 11th degree polynomial. Let's see what this is maybe in vertex form real quick, because that's going to help me learn a bit more about what this value x needs to be. Converting this to vertex form, I would get t minus 1/2 squared. Distributing this all out gives a plus 1/4 kind of built in there. So maybe I could do minus 1/4, and this would be the representation here if x were 0. So I could just maybe pop on a plus x. Basically, I'm claiming that this expression and this first part are the same. Now, it's likely that we have, or it's confirmed that we don't have two x-intercepts, t-intercepts. Maybe we have 0, maybe we have 1. In the case that we have one t-intercept, this value right here in vertex form would need to be 0. That would help us rest right here on the t-axis. So it's possible that x maybe is 1/4 for this problem, but here this doesn't make sense because it says that x is an integer. If x were negative, then we'd be pulling this quadratic lower on our graph, and that would then have two t-intercepts. So the only possibility is that this x is greater, not lower than 1/4. And like maybe in some sense, a negative value of x could make sense because we could very well have two numbers. They both are negative, perhaps, that multiply to a positive 90. However, kind of this graphical thinking or graphical explanation shows that x must be positive so that we don't have any t-intercepts out of our quadratic right here. And there's actually another strategy that I'd like to try to kind of pare down the possible values for x that we have. And it's essentially just going to be plugging in some values for t and seeing what happens. I showed earlier how our big polynomial, which I'll just call p of x, should be equal to our, p of t, not p of x, should be equal to our original polynomial, I'll call that f of t, times some other polynomial. This is that degree 11 polynomial. I will just call it q of t, q for quotient, because that's what we get when we would divide p of t by f of t. And let's see what happens if we set t to some easy values, say 0, 1, and then -1. When t is 0, we would get f of 0 times q of 0 is equal to p of 0. And p of 0 is just plugging in a 0 into here, so that's the number 90. And on the right side, f of 0 would knock these off. We would just get x. And then I don't really know what q of 0 is, but that's fine. This shows me that x is some factor of 90, right? Because x times something else is 90. X must be an integer from the problem statement. So we do get x as a factor of 90. Now, we already saw that, but what we didn't see is what follows when we try plugging in other numbers. When t is 1, we get 1 plus 1 plus 90, so p of 1 is 92. And then up top, we have 1 minus 1 plus x, so just x. X times, and then whatever q of 1 is. This shows us that x is a factor of 92. Now, 92 has, other factors as well. Like there's 1, 92, there's 2, and then 46, and then so on and so forth. We could draw out that whole list. But the interesting thing here is that x is a factor of 90, x is a factor of 92. And if a number is a factor of two other numbers, it must also be a factor of the difference of those numbers. Like, for example, if say 5 is a factor of 15, I'm showing that here. 5 is a factor of, say, 50. Then 5 must be a factor of the difference between these two numbers. It's really clear if you just look at it because it's 35. But I can prove it by, say, factoring out this 5 from both sides and doing 10 minus 3. Anyways, if x is a factor of 90 and 92, x also must be a factor of their difference. And this leaves us with just 2. Or in other words, x divides 2. We could also think of it as a divisor. And this limits our search considerably. X could be maybe positive or -1, or positive or -2, and that's it. And actually, earlier in the video, we did talk about how they can't even be negative values. So we do just get +1 and +2 as our possible values for x. So that dramatically decreases our sample space here. I think if we plug in the -1, we will get the last little piece of the puzzle. Plugging in the -1 here gives us -1 minus another 1 plus 90. So that's going to be 88. 88 is equal to, this will be 1 and then minus -1, so 2. 2 plus x, and then times whatever q of -1 is. And let's take a look at what it might mean if x were 2 or 1, because those were the only two possible candidate numbers from our divisibility checks from above. And if we try plugging in x equals 1 right here, we get 88 equals 3 times q of -1. Now, this isn't going to work. 3 is not a factor of 88. We can maybe see this by the fact that the nearby multiples of 3 are going to be 87 and 90, so it just won't work for 88. And therefore, we have, by process of elimination, ruled out everything except for 2. And actually, we're done. We don't really need to do the division. Just by kind of checking a few values for t, we've dramatically limited our possible values for x down to just 2, as in down to one possible value, which is 2. So I guess we're done. Though if you wanted to see that it actually divides it, why not? We could run through one of our division strategies. I do briefly want to share what didn't work before I realized those like divisibility rules. Here I was trying to do an area model. You can see here's f of t, this is q of t. I was placing their coefficients along the sides of my area model. And the only reason why x is showing up everywhere is because here I didn't know that x could be 2. I just wanted to see if the area model was going to give me any information if I didn't know what x was. And so I was, multiplying all these things. As you can see, I started running out of space, and so I gave myself more room and started writing more polynomials. And it just became a whole jumbled mess, and I couldn't really use it. What's kind of interesting is that it does kind of work. Like I was able to create some kind of degree 6 polynomial that was supposed to go in this square. I set it equal to 90. It told me that x was equal to 2 and then also like 3.7. So it kind of worked, but it relied on me solving a degree 6 polynomial, which I just did by graphing. Anyways, this didn't work out so hot, and I will try another area model to kind of redeem myself. But at least this area model that I'll show you, is when I already know that x is 2. Here's my setup for the area model. I have my f of t polynomial on the side. The top is blank because I don't really know what q of t is going to be at all. I mean, I do know that to get t to the power of 13, I will have t to the power of 11 as my top number. Knowing that x is 2, my 90 over x is going to be a 45 at the end, so that's kind of cool. But then let's fill in the inside part here. So we do have a t to the power of 13. We do have a 90. And then the only other information that I have is that these two squares must sum up to, well, actually nothing, because we don't have a t to the 12th term. We're going to fill out the whole table, and then hopefully these last two squares, or I guess rectangles, will give me this plus t in the end. And let's just see what the area model tells us. So this t squared, and knowing that the target was t to the power of 13, told me to put a t to the 11 up top. And now I'll multiply this through to figure out the next two values in my area model. This will be minus t to the 12th, and then plus 2t to the 11th. Now I don't have any t to the power of 12 terms in p of t, and so this term must be t to the power of 12, and then therefore, using this information, I do know that the next term in q of t, the quotient, is going to be t to the power of 10. Now I can use that information, multiply through down, I get minus t to the 11, and then plus 2t to the power of 10. And this process kind of keeps just going on. Here I know that there is no t to the 11 term, and so to make sure that this zeroes out, I do need a minus t to the 11 here. This requires a minus t to the 9 on top, and then I can multiply this through, and let's just see where this takes us. All right, at this point, I do recall that these two need to add up to be a positive t. So let me kind of break my pattern of just doing what I'm doing and kind of jump here first. So this should be a minus 45t. And then let's see, oh, well, actually, yeah, look, this 45 that we already kind of knew about does multiply with this negative t, and so this checks out. And then let's just make sure that that top right corner also makes sense. Looks like we have a minus 22 and a minus 23. So to balance that out, again, we don't have a t squared term anywhere here. I do need to add 55 t squared. Wait, nope. I was really worried there for a sec because the 55 didn't match up, but I just did math wrong. That's going to be 45 because 23 plus 22 is 45. So plus 45t squared. This and this line up with that box. Then we do get these two terms totaling to just t. And then finally, we do get a 90 in the end. So here is our original polynomial. we can see in standard form expanded all out. This is the same thing as our original degree 13 polynomial. All of these diagonals just cancel out to, even this one, to just so many zeros in here. And then finally, we are left with t and then plus 90. And so if you wanted to know, this is the quotient we get after dividing one polynomial by the other. And we have no remainder. Wonderful. So it does divide in evenly. So that's the answer. This is our polynomial, and we are all done. So thank you for watching, and I'll see you tomorrow. Bye.